Good evening, everyone. Hello, my name is Heather Segali with the UC Davis Tahoe Environmental Research Center. Welcome to our return to in-person events. This is very exciting. With this return, I want to remind everyone to turn their phones to silent or something like that. You know, since we haven't had a lot of in-person events, that might not be something you remember. So I want to learn more about TURC and the research of the Tahoe Environmental Research Center and our events. You can go to our website at tahoe.ucdavis.edu. We also have citizen science programs. We have school programs for kids. We have science center tours. You can sign up for a registered tour. And let's see, you can also find out how to follow us on social media. If you're not already receiving our emails, you can sign up to receive our emails and learn how to participate in all the other upcoming events. The other upcoming events that we have on August 4th is a special event. Dr. Glenn Fox will be talking about beer's impact on civilization, and that will include beer tasting. And Alibi Ale will be providing the beer, and that's a catered event, so it's a slightly different than this format. And that is August 4th. On August 11th, it's microclimate diversity and lesser known varietals with Boger Winery. And then on August 18th is international cheeses paired with local wines. And I just put in the cheese order to be delivered closer to the date of August 18th. And the list of cheeses are very unique and interesting cheeses. And Dr. I'm going to say it wrong, Moisha Rosenberg, perfect, all right, who is a cheese expert on the UC Davis campus, and he'll be talking us through cheese tasting. And we've done it before. It's incredibly fun. All of those are very fun. So I recommend all of those. And I would like to invite Tim Kozer, one of our advisory board members, up to continue with the rest of the introduction.
Thank you. All right, I'm Tim Kozer. I've been a docent here for 10 years now, and also chair of the advisory board. So, but I want to let you know that UC Davis gives us good support and funding for the base. But in order for us to carry out the research, education programs like the Red here and things that we've got at the Education Center, we need philanthropic help. And so I encourage you to making sure that you check your savings account. There's still some in there. We would like to see that someplace. You can see me afterwards. We actually have some literature here. And sitting over here to check you in is Tony with the striped dress over here, and she's at the development office of UC Davis. So I want to put that picture. So in addition to that, it's my pleasure to introduce Dr. Jeffrey Schladow. He's a professor of water resources and environmental engineering at the University of California, Davis. He's founding director here at the UC Davis Tahoe Environmental Research Center, TURC over here. And we hope that even though he's founding director, he continues to be director until he reaches the age of Dr. Charles Goldman today. So TURC is producing the critical scientific studies and predictive modeling that is underpinning the restoration of Lake Tahoe, lakes and high mountain regions subject to climate change and other human forces. And that's not only true in the United States, but it's also doing work worldwide. For over 30 years, his research has been focused on the interactions between the complex fluid motions found in nature and their impacts on water quality, ecosystem health, and watershed processes. He has published over 250 research papers, and technical reports, and has guided over 75 graduate students. Many of you may not realize this, but here at TURC, sometimes people refer to Jeff as the Mark Twain of TURC. Now, what I want to be sure you understand, that means he's got a good sense of humor as opposed to starting fires at North End. To be Dr. Trump.
Great. Well, thank you for that kind introduction. Tim, I actually think you look a lot more like Mark Twain. Okay, well, it's great to be here. I'm a little rusty. I've been talking to a monitor at my dining room table for 2 years now. But it's good to be here in front of you all. I see a lot of old friends. I see some older friends, which is good. It's so anyway, I need the pointer, which is in my pocket, and I'm going to get going. All right, so before we start, so yeah, this is the state of the lake report. We get support to actually put this report together from a number of people. So we have the logos shown here. I just wanted to acknowledge them because it is a big production for many people. And the other thing I wanted to acknowledge is that I'm the one that gets to stand up here and say, what we did, but there was a real we there. It's not me. And so we have this incredible team. Actually, this isn't even all of them. Some two actually sent in their photos. So they're great. Some are based here, some are based in Davis, some are in Arizona. They're all over the place these days. But without them, we just couldn't do anything. All right, so amazing how time flies. This is the 15th State of the Lake report. It's not the 15th talk. So it took us a few years to realize maybe people would be interested in this. So, but 2007, we thought we put this together. So we collect all this data, and up until about 2007, we were just looking at it ourselves, thinking, wow, this is so interesting. And realize well, maybe other people would find it interesting, and maybe it would be a good exercise for us to put it all together and try to explain it. And it's been this incredible exercise and this incredible journey. So make a couple of things clear at the outset, and that is, this is our annual attempt to present our most recent data in the context of over 50 years of science at Lake Tahoe. So some of you may say after listening to this, well, 2 years ago, you said the opposite. Well, yeah, that's what I thought 2 years ago. But my knowledge changes, what we've learned evolves, and things change. What also changes, which is important to realize, is the lake. The lake and the watershed, the people, the population, the local population is way larger now, not the permanent population, that's going down. All the Airbnbs and the people who are using the resources, the lake, the land, that's never been more intensively used than now. So what we're seeing is evolving with all these things, climate change, land use change, and what we're learning. And the second point here, this is not a score exercise. Don't wait till the end when I say, the judge's decision was a top of 63 this year. There is no score. There are no A's, B's, or C's. This is what we believe we're seeing, what we think is happening, and more importantly, this is where we think we as citizens, those who are in management agencies, implementation agencies, the people who can actually implement change here, this is what our recommendation is to them. They, of course, have to weigh our recommendation with lots of other recommendations and lots of other constraints that they have. Okay. So this is a big report this year. And you don't want to see it all. Trust me. Well, actually, you do want to see it all. You don't want to hear it all from me. So the report's online. Our website, tahoe.ucdavis.edu, it's there. What I'm going to touch on tonight is just a few things. There are a few important things in there that aren't going to get the amount of time they should, because there's a story, there's a narrative I want to focus on. So these other important things, I'll defer to you to, if you're interested, to read about them. So one of them is the work we've been doing on microplastics for the last few years. This is a collaboration We have with the veterinary medicine down at UC Davis. In a nutshell, we were curious. Are there microplastics in Lake Tahoe? Are they at the top, at the bottom? Are they in the water we drink? And we all say, yeah, drink to Tahoe pure. Are we drinking? We don't know. What about all the animals in the lake? Are they ingesting these particles, or are they taking out plastics? So anyway, we're sampling, we're filtering. These are some of the larger scale particles. You can see this is a Raman. This is using Raman spectroscopy. Bottom line is seasonally, these are the particles we counted in the lake. In over 1 million square kilometer. Nobody thinks in terms of millions of square kilometers. The important point is, this is a similar number to what people are collecting in San Francisco Bay. And that sort of took me by surprise. What are the plastic particles? The usual suspects: polyethylene, polypropylene, polyesters. But I'm not going to talk about that. I'm also not going to talk about the forests. So this is a photo I took as part of our circumnavigation of Lake Tahoe a few weeks ago. This is the west shore of Lake Tahoe. And I was stunned by the number of dead trees. Since one, but they're white firs primarily. But look at them, there are thousands. I mean, there are thousands in this image, and this image is just a small part of the west shore. So there are tens of thousands of dead trees. Why are they dying? Well, we're in a 10-year drought, so there's not enough water. Certainly one reason. Without water, trees get weakened, and so they're more prone to insect attack, pathogen attack. Aside from being unsightly and not what we imagine our watershed to be, this is a human threat. These are bottled dead trees. This is fuel waiting to be ignited. There are plans for what's called landscape scale. So that's the landscape scale tree removal, that's called. Not just removing a few acres, but removing trees in the whole west shore and the like. Those plans have been around for a while. Doesn't seem like a lot has been done as yet. What can we do? Well, we can't make it rain. We hope it will rain. We're doing other things. So as you look at this image, you see the dead trees and you'll see the green trees. So side by side, you have two trees. One's doing just great, the other one's dead. Same species. What makes one stronger, more resilient? We don't know, but there's something in its genetic makeup. So what we do is collect the seeds from those trees, germinate them, keep them in our lath house here, and then with collaborators like the California Conservation Corps, we replant them. We don't replant them in the middle of all of this, where there are way too many trees, but where there have been fires, where there have been burns, where revegetation actually is needed. All right, I'm not going to talk about forests. I'm not going to talk about invasive clams at Sand Harbor, other than to say they're there. So Sand Harbor, one of the most beautiful beaches, shorelines here at Lake Tahoe. The map here, this is the main beach at Sand Harbor. This is the boat ramp here. So a few years ago, they had Asian clams, so Collicula fumigera is the proper name. They were treated, put rubber mats out there, they controlled it, but you can never totally eliminate an invasive species. So for the last few years, we've been working with the Nevada Division of State Lands, and we've been mapping where clams are now. So these colors you see here are the densities of clams. So the The yellow colors, see that, the yellow colors are very high values, the blue colors are low values. So here, a lot of clams, over 300 clams per square meter there. These bluer colors, it's 10, 20, 30, something like that. But this is where they were. This is the treated area. They're growing. They're expanding. Is that such a bad thing? Well, yeah, it is. Aside from being uncomfortable and unsightly, they produce other problems. So what you see there is metaphyll. This is a filamentous floating algae that accumulates wherever we have clams. The clams filter the water, they concentrate the nutrients, and that's what you get. So without trying to sound like the end of the world is here, Sand Harbor is still very isolated, this metaphyll. South Shore, it's all over the place, but this is the fact that it's beginning already. At Sand Harbor is a concern, and we're hoping to work with the state of Nevada to come up with mitigation measures. This is something I'm really proud of. We have measurement stations all around the lakes. We have models that predict what the waves will be, what the currents will be, the temperatures. So we work with a group of undergraduates at UC Davis to take that information and our measurement stations and our models and create pretty much a warning system. We call it just don't do it, meaning don't just jump on your paddleboard and go out there until you know what the conditions are like. It may be a perfectly calm day, but if yesterday was windy, you may have a situation where half the lake is 10 degrees colder than the other half. Nobody here would fall off a paddleboard. But if somebody from the flatlands, from Davis, came up with paddleboarding for the first time, they will no doubt fall off. When you fall off, and instead of being 65 degrees, it's suddenly 50 degrees, you go into shock, you have hypothermia, and by the time you get your breath back, your paddleboard has drifted 30 feet because you're too cool to wear an ankle tie. So the idea is check the conditions. Every year, over a dozen people drown here. Many of them young and fit, they have no business drowning. And if we save just one or two lives, that's great. And finally, everybody's favorite lake monster, Tahoe Tessie. She's not real, but climate change is. And so this fall, we have a new augmented reality app that's going to be released. We hope it will be released for this summer, but things always take longer than we plan or we hope. And what you'll see if you get into it, if you play with it, is the impacts of climate change on Tahoe Tessie, which are remarkably like the impacts of climate change on lots of other animals and things that live in Lake Tahoe. All right. So I've been doing this for a while. This is probably the 10th such presentation I've given. And this one is probably, I think, the most, what's the word?
Depressing?
Sorry?
Depressing?
It's not depressing. No, it's not depressing. It's scary. It's different. There are bigger changes happening. There are bigger changes that happen in 1 year than in most other things I've spoken about. So it's coming. So something, actually coincidentally, many of the things that I usually talk about haven't changed much at all. So a lot of this is new to me as well. So let's run through some of the things that are pretty much as expected. You don't need me or UC Davis or Turk to tell you about. The weather's getting warmer. You wouldn't have known that, would you? I mean, this is going back to 1911. These are our maximum temperatures, these are our minimum temperatures. Fact of life, I think we're used to it now. I mean, used to the fact that it's getting warmer. I don't think we know what we're we headed for. There was less precipitation in last year, in 2021. Again, this is data going back over 100 years. This is the average precipitation. This is where we were in 2021. And if you've been paying attention, this year's been even drier. So it's dry and it's warm. It's all due to climate change. Because it's warm and it's dry, the lake level's falling. So this is lake level for the last 3 years. So this is 21 to 22. This dashed line is it's called the legal limit. It's the top of the dam. If we reach that level, all hell breaks loose. Uncontrolled flows down the Truckee River. This is what's called the natural rim. That's sort of the natural sill of the lake. At that, when water level flows, so it falls below that, water no longer flows out of the lake, which means goodbye rafting businesses. But that's probably the least of our worries. So here we are this last year. Normally it's in the spring, we get a boost in water level. Basically didn't get that. So it went down back last October, November. We just touched the natural rim, and then you may remember rain, we had snow, everything was good. Don't see it now, but the level came up to about here this year, and probably in the next 2 months, it will go below the natural rim. The lake's getting warmer. Again, we all know that each of these bars represents the annual average surface water temperature. What's interesting is we wrote a paper about this back in 2007. So at that point, this was the data we had. Back then, that was sort of a big deal paper. Oh, it was getting warmer. And there only been 2 or 3 papers written about lakes. And now every lake's getting warmer. That's no longer news, but it hasn't changed. It isn't a cyclical thing where it goes down again. Yes, there are ups and downs in different years, sometimes for a few years, but that trend is continuing. So they're the things that used to excite me and used to excite you, but it's just, you told us that last year, you told us that the year before. Okay, now I'm going to tell you something totally different. So, biologically, the lake was very different in 2021. Maybe scarily different. I don't think it's scary. I think it's exciting. Because I think it's giving us opportunities that we've never had before. Bear with me. Okay. So I should, I guess this goes to be the fine print at the bottom of your TV screen saying, this person is not a biologist, even though I'm talking about the biology. Okay, I'm going to talk about 3 kinds of biology. First of all, I'm going to talk about the attached algae, the stuff that grows on rocks around the shore. That's called periphyton by people who are biologists, people who pretend to be. Secondly, I'm going to talk about the algae we really don't see because they're tiny and they're out there in the middle of the lake, but they're there and they float around with the currents and they're actually called phytoplankton. Plankton means that they're just carried around by the currents. And then I'm going to talk about the microscopic animals that are in the lake. The zooplankton, they too, they can move a little bit, but generally they move with the currents. Okay, so the nearshore attached algae, the periphyton. So for many years, 20 years, 25 years, UC Davis has been monitoring these attached algae. So this is a very time-consuming, laborious process. So we have a number of sites around the, I say we, you know what I mean when I say we. I say we, I mean them. The ones who do this. We go around to maybe 8, 10, 12 sites around the lake every 3 to 4 weeks, We measure the growth of algae on those rocks. Some years it's more, some years it's less. Long story short, after 20 plus years, it turns out it's not growing any more or growing any less. It hasn't changed. Okay, well, that's information. Yet when you talk to people, they say, oh, there's algae, they're everywhere. When I was a kid, there was no algae on the rocks. It's clear as gin, they would say. So what we've been working on for the last few years is the idea of a different way of trying to monitor this. And that's to monitor it aerially, either using drones or using helicopters. The advantage of drones is you get really high resolution. The advantage of a helicopter is you can do the whole lake in an hour and a half. So rather than spending days and days of people underwater scraping algae off rocks, you get a measure of the whole system. I want to have a shout out to Mike Bruno. Mike Bruno is one of our board members. It's actually his helicopter. A lot of this, what's behind this project is his enthusiasm. In many cases, his funding and then the funding of his friends. But what it's turned out to be is a tremendous new tool. Okay. So I want you to look at this. So this is the northwest corner of the lake. This is Tahoe City here. And you see there what looks like a photograph. Next to it, there's another photograph, and then another photograph. So these are all images from the helicopter. Flies around 1,000 feet, taking all these images, moving around, bobbing and weaving. But then what we're able to do is to stitch them together seamlessly. And once we've done that, we just focus here, which is an area that covers, say, 2 of these photographs, we come up with an image like this. This also mosaic of the area around the outlet of the Truckee River. This brown stuff you see, that's attached algae. Most of this wasn't near any of our measurement sites. It's probably growing at a similar rate to our measurement sites, but for the first time, we know where it is. We can use these images not just to get a pretty picture, but to quantify how many square miles this is covering. From month to month, is it growing? Is it receding? We would love to be able to remotely tell you what kind of parasite it is, but to do that, we have to go out and ground truth it. So this is a picture from the same image. This is showing what the rocks right close to shore look like. And you can see, hopefully, that they're green and they're slimy. It's a mixture of stalk diatoms, and it's a mixture of that and green filamentous algae. So this is turning out to be a lot more efficient time-wise. And second of all, it's giving us the information that is useful. We sort of established that the growth rate is what it is at a particular location. Is it growing at other places where it wasn't before? And why? Is it the lake level? Is it the stormwater that's coming in? Is it human activity? I'm not sure. Okay, as I say, these images, these are some of the most extensive and thick paraphyton blooms that we've seen. All right, that's the algae on the shore. Okay, let's talk about the algae in the water. Stuff we don't really see. Just Tahoe actually has very few algae, very few phytoplankton. That's why it's beloved. Okay, I'm going to show you data from 2020. What is this data? Okay, so first of all, this is data by month. January, February, March, it was too cold, nobody wanted to go. And so on and on we go. What you're seeing here, these different color bars, the colors represent the kind of alga it is. So you see most of them is this gray color. What's gray? Gray are diatoms, which are the dominant alga in Lake Tahoe. Diatom has a little silicon skeleton, and then it has its biomass on top of that. The diatoms and so on. So the peak was in about April in 2020. What else can I say about that? Nothing. Okay. Disturbing thing number one. This is 2021. Go figure, as we say it. Forever. It's like, it's totally different. So, well, it's still the gray stuff, it's still the diatoms. They are the maximum on the basis of biovolume. What's biovolume? Biovolume is just the volume that algae take up. So literally, you just figure out what the volume of it all is, and that's the biovolume in cubic millimeters per cubic. Basically, parts per billion is what it is. So this is the biovolume of diatoms. That's the biovolume of green algae and so on. I should add, I asked the question when I saw these data, well, is this pretty typical? 2020? They go, oh no, it's usually lower. So this 2019 had half as much as 2020. So these peaks are literally 6 times the baseline. Okay, so these are the highest algal abundances we have measured. I guess we've been doing this for 54 years. I guess 3 times higher than last year and 3 times and double the year before. Okay, I'll say, well, that's interesting. It changed. Okay. You're all curious people. You're all, I can tell, you're thinking, what causes? So, you know, algae are like, it's like your lawn. You need nutrients to feed it. So you put fertilizer on your lawn, lawn grows. Duh. Put nutrients on algae, algae grow, right? These are the nutrients coming in from the watershed. This is from 1989 through to 2021. 2021 for nitrogen, lowest on record. It's a dry year. Doesn't make sense. Phosphorus, the other key nutrient, lowest on record. This year is going to be lower, but it's hard to think that these incredibly small inputs of nutrients cause the phytoplankton to take off. I can't see a connection. So what else could it be? The idea is what else happened in 2021. We might have had a nutrient. Wildfires? Ash, wildfires. Good idea. We measure that. Actually measure the nutrients coming in. It's called atmospheric deposition. So yeah, we had huge fires. We're going to keep having them. That's what it was like out on the lake. This is just an image showing the smoke and coverage over the lake. So that's a great idea. What's bad about it is the timing is wrong. Smoky from August to September. This is what we can't explain. Nice try, John. Sorry. No free drinks. All right. So we're going to come back to this. I'm going to put this discussion in on hold. We're going to call this the paradox of the algae, because we don't know what caused it yet. We hopefully will by the end of tonight. The paradox of the algae. Okay. So the algae is also, I haven't finished with the algae phytoplankton. So we also, there's another way you can measure algae. It's in several ways. Let's talk about 2. So we are talking about measuring their volume, just what the volume is, but you can actually measure how many of them there are. Because with many things in nature, there are often way more of the very small things than the very large things. So that's one thing we do, we count them, especially because at Tahoe, very small things are what impact the climate. So we're now looking at a graph that's showing the percentage of the annual total number of cells. What do I mean by that? This is the data, different years. Now we're just going from 0 to 100%. So if we just look at 1982, what this is telling us is that in this year, about 50% of the number of cells were again the gray ones, the diatoms. And then 10% were the green ones, the green algae, the golden algae. So that's how every year is painstakingly divided. If you look at the whole pattern, you see, well, some years there's more of one and less of the other. Till we come to 2021. It's totally out to lunch. It's this dark green color. What's dark green? Dark green are blue-green algae. So we've had some of them before in the past at different times, but we've never had any algal group that represents like 90% of the cells of the plant. This last year, blue-green algae. Some of you know a lot. I know that. And some of you know so much. You say blue-green algae, aren't they cyanobacteria? Aren't they harmful algal blooms? Are we going to die because they're toxic? Well, some of them are. This one isn't. So I'm not trying to raise a flag about Tahoe is becoming toxic. It's just a cell from that family. Actually, I'd like to meet the person, the cell responsible. So this is Leptolimbia. So these little filaments, these little strands, are Leptolimbia. They're actually, each one is a tiny little 1 micron cell, and they just form these strands. These are hundreds and hundreds of them put together. So what we know is from experiments we did a number of years back, is that they like the high nitrogen to phosphorus ratio you get with wildfires. So it turns out that these Leptolimbia actually did respond to the wildfire smokes. John, you were right. So these grew exponentially between September to November, exactly when we had the smoke in the area, nitrogen to phosphorus ratio, we believe is what prompted that. Okay, I think we've had enough fun. Zooplankton. Okay. So this is showing the primary phytoplankton. Zooplankton we have at Big Tahoe. So this is not the scale. But their relative scale is not the same. So this is the Mysis shrimp. So this was an introduced species, was introduced in the 60s. They thought it was a good idea, would make the fish larger. It was a bad idea, made the fish smaller. What it also did was it ate Daphnia, which is the native zooplankton, and Bosmina. These are what made the fish bigger. That's right. This is what fed minnows, which the fish then ate and grew bigger. Mysis came, devoured them. They're gone. What was left were these tiny little Leptospira and Diaptomus, collectively known as copepods. Everybody remember that? All right. This is so good now. All right. Data points.
Rest around, take her.
I've never seen this woman before.
Data is too shocking.
All right. Somebody's trying to distract me. Data from 2011 through the middle of this year. So normally we always stop at the end of the year, but this is so interesting. We could not help ourselves. We just kept going. So there are two graphs here. One is the Bos minor, the red ones. The red one, the Bos minor, that's what the mysis almost drove to extinction. And you'll see extinct, well, 0, 0, 0 up, they're free air, 0, 0 up, they're pretty much where they've been since the mid-60s, late 60s. Okay, the copepods, they're the Apiaceae, Aptimus, there's tiny little things, get a dozen of them on the head of a pin. They're invisible. Okay, they have their ups and downs. A lot of these ups and downs are the fact that is their breeding cycles. They breed in the spring. You may have seen them if you walk around between the rocks on the shoreline in the spring and you see those clouds of little red things floating around. They're the Apiaceae. This year you would not have seen them because they weren't there. So these blue things up, down, up, down, up, down. Suddenly, in the 21, 22, barely there. Okay. Am I worried about this? Not too worried. Maybe because there have been other times when they've been near zero and bounced back. So I expect them to bounce back pretty quickly. All right. ISIS, unwelcome intruders from a half century ago. Same stuff, up, down, up, down, up, down. Look at this. They had gone to zero, pretty low from about spring of 2021. What is this red dashed line? This red dashed line is the level. As they get below that, then pretty much there are not enough of them that all the other things could start coming back. Okay, so the last 6 months, 9 months, mysis have been absent, close to zero. Because they live for about 4 years in the lake, all of the classes, year classes are absent. It's going to take them some time to get back. They will get back. If there anybody here who loves them, fear not, they will come back. Okay, let's go back to the paradox of the algae. 2020, it's not a low year, spring bloom there. This is about 2021, they're high here in spring. Why are they high? Mainly because they grow by nutrient addition, but they get eaten. They're delicious. Mysis love to eat them. So what I'm suggesting, hypothesizing, is maybe it's the absence of grazing by mysis. The mysis, this is the time when the mysis disappear. There's nothing eating them, so they just grow uncontrollably. Uncontrollably. I mean, it does go down, but that's because they use all the nutrients and they do run out of the nutrients eventually. So this is what I think is explaining stuff. We said before, there was a diatom that was most of the biovolume. That's Synedra. It's big. I mean, it's like 60, 70 microns. It's huge. Something. Not huge at all. I mean, the thickness of a hair is 100 microns. So its great enormous length is less than the thickness of your hair. So essentially, it's a large enough size that they could chow down on that. They think that's great. That's like eating pretzels for them. So they eat those. And so that's what I believe occurred. Okay, I've underlined this. Once again, mysis is associated with a large change in the biology of the lake. Once again, like has this happened before? Well, it's happened twice. So the first time it happened is when they were introduced in the 60s, came in, the numbers went up over 5 or 6 years. The Daphnia, which are just natural cleaners in the lake, crashed, disappeared, rarely been seen again. So we know that. There's literature on that, it's happened in other places. Mysis screwed things up. But there was another time they screwed things up too. That wasn't in Lake Tahoe itself, but it was in Emerald Bay, which is literally another lake just separated by a shallow sill. So this was between 2012 and 2018. So let's run through what happened. So 3 graphs here. So this is showing 2 years, from 2012 to 2014. These dots are the numbers of mysis. So the mysis are really low again, down in Emerald Bay. This is their average number, but they were way below. Because they stayed low for long enough, the Daphnia numbers went from 0 up to 3, 4, and 5,000 cubic meters. They took off. Daphnia population rebounded. Amazing thing is, the second depth in Emerald Bay went from 40 feet to 70 feet. While this was happening, in the absence of mysis, Daphnia, the native zooplankton, came back. Clarity improved. Okay, let's finish the story. Eventually, the mysis do come back. We sort of hover around their long-term average. The Daphnia drop off back to their long-term average, and the clarity goes back to its long-term average over a period of 5 or 6 years. But in the middle of this period, there was a 30-foot clarity increase in 2 years. Okay. So let's talk about Tahoe and its clarity. So this is what we've been measuring. Some people think this is all we do. It isn't. So each of these dots represents about 25 values of the Secchi disk. It's measured how deeply we see it. And we average that each year. So back here in the late 60s, you could see down 30 meters. That's about 100 feet. And ever since that time, it's been declining, how far you can see that. Lots of variability taking place. Over the last 20 years, despite lots of effort, lots of money, lots of good intention, lots of science behind what was being done, it hasn't improved. And you can run statistical correlations through this. It's neither improving or decreasing, it's flat, no change. Okay, this is like my predictions. I like making predictions. But based on what we're seeing with the mysis now in Tahoe, resting on what happened when they were first introduced and seeing what happened in Emerald Bay, we think the conditions are there for these things to happen. For the mysis populations to stay low for 3 or 4 years, till it eventually comes back. For the Daphnia, the buzz minor, I don't say when I say it should be 22 or 20. Yeah, it's 23 and 24 next year to come back. This is a big one. I think clarity will come back 20 feet in the next couple of years. What does that mean? So this green dashed line represents a 20-foot improvement from sort of where we are now. That means we'll be back to where we were in the 70s. I wasn't born then, so I don't know what it was like. Okay. So some of you may say, well, that's an interesting experiment. Maybe you're right, maybe you're wrong. We'll see. But let's say it's right. Let's say that happens. Eventually, the mice are going to come back, and we'll be right back where we started from. So how can we sustain it? Some of you have heard this before. Some of you may be hearing it for the first time. So it turns out that mice are actually pretty healthy to eat. So if you look at the lipids in them, they're actually something like a third omega-3 fatty acids, which we all buy these pills from Costco and Walgreens and everywhere to keep us young, alive. If we compare that with, say, salmon, which the ones from Costco come from, they only have half that omega-3. So these are really, really helpful. So we could market them. We could give them to you every time you came to a lecture here. We could buy them. But we'd probably be imprisoned because they haven't been FDA approved and all those things, which will take 20 years. So sorry, we'd like to do it, we're not going to. But the FDA could not care less about your dogs. So we can make dog treats out of these, healthful dog treats. We'll be working with this nonprofit that was created out of the Business School of Management at UC Davis called Shrimply Blue. That's mission is to really educate the public about Lake Tahoe and clarity and preservation of all natural systems through their dogs and through giving away these treats. Done the research, markets there, and it could happen if the mice came back. I mean, right now, this business, we're not invested in this business. There will be mice. Dogs are unhappy, but they will come back. And financial models show that once you get this up and running, you can break even, keep the whole thing going. All right. So, Heather said this is going to be a depressing story. I think it's invigorating, it's uplifting. We have an opportunity. Glass is half full, maybe 3/4. So the stage has been set for us to understand all these things I've been saying. I said lots of maybes. I think this could happen, this should happen. We don't know. Now, forces larger than any of us have cleared the mice out of the lake. The lake is going to start responding. We're going to start seeing through the Daphnia come back. What are they eating? Are they eating tiny little algae and tiny bits of dirt that cloud the lake and reduce the clarity? That's what we think. We don't know that. We're going to have the conditions created to evaluate that, to see how the biology links with the clarity, and with all the other things that are happening that we have no control over, like wet years and dry years and climate change and all those things. So this is an opportunity for us, and I'm talking about us, the greater community, which includes agencies and regulators and all those sorts of people. So these are the things, these are all the things that are in play that we have a chance in the next 2 or 3 years with the appropriate monitoring to learn what we what we need to know. I'm including fish here because this does affect fish. And actually, this monitoring has started. We're working with fishing guides, and they're doing us a favor. They're giving us fish guides, but it's very important because the fish guides they give us tell us what the fish are eating. So they're putting them in the freezer, and then we're going to analyze it. Coincidentally, right now, I'm told that the lake trout when they look at their stomach contents, there's nothing in there. They're not eating. They're normally eating mysis and a whole range of other things. There's very little food to them. The kokanee, which are closer to the surface, have a lot of terrestrial insects in their stomachs. They're not eating the usual things because the zooplankton all down. So we're starting to learn a lot from that. So anyway, current biological monitoring of Lake Tahoe is sub-minimal. There's a lot of physical modeling, streams we monitor, temperature, clarity, all these things I've been talking about. It's not happening. What the data I presented, most of it, not all of it, the agency funds some of it, most of it has been through philanthropic gifts, things like that. The reason we're able to go out and sample the mysis, nobody is paying for mysis sampling. And it's not easy because you can only sample them at night when they come up to the surface. And so it's a lot of work. So if we can get the funding, I'm hoping this message will get through. I think we can learn a lot. Without this funding, we would not have known the mysis had disappeared. Imagine that. Let's say we didn't have this data. And Russ Weigart works for El Dorado County, and he's one of the people really concerned about clarity and what drives it. And every year he gives me his prediction of what the second depth will be, and he is annoyingly accurate. But let's say we didn't know mysis had disappeared, and let's say, perchance, clarity improved 15 feet next year. Russ, can you imagine the theories we would come up to explain that? All of them would be wrong because we didn't have that, but we didn't know mysis had disappeared. Okay, so with that, I wanted to thank you, and I'd be happy to take any questions. Francis.
So I wasn't paying close enough attention in the graphs that showed mysis concentrations over the years. And there, aside from the time that it happened in Fang, are there other years where the mysis crashed in the lake as a whole?
Not that we know of. Everybody was interested in mysis in the 70s until about 1980, and then it was like, okay, they're there, we can't get rid of them. Let's move on. And so there was no funding, or even less funding for mysis. So we don't know. We don't know what happened. Maybe a good year in clarity in the 90s, we put down to who knows what. And it may be mysis. We just don't know. There's zero monitoring. But for the years we have, which is primarily from 2012 onwards, this is the only, in Tahoe, this is the only sustained, meaning 9 to 12 months, mysis redlining.
Maybe they'll never.
Sorry?
This is maybe they'll never come back.
No, they'll come back. They will come back.
Why do you say that? That was part of the question I was going to ask. What factor do you think is at play that will bring that population back up?
Because
Can you repeat the question?
I repeat the question. So the question was, well, what makes me so confident they will come back? And it's because this is nature. It's really hard to get rid of something completely, especially something you don't want. It will come back. Anybody who's weeded their garden knows that. So they will, I believe, because the fact that there were a very small number were introduced, and within 5 years, they were the dominant animal in the lake. And despite their ups and downs, they've been here for 55 years. They're gone now. I would be very surprised, shocked, if they didn't come back. Do I know for a fact? No. Martha.
Are there other places where mysis are being monitored?
Are there,
Are there other locations in which mysis are being monitored?
Well,
Oh, other locations, sorry, the question was, are there other locations where mysis and zooplankton are monitored in other lakes? Oh, sure. They were introduced throughout the West. Because it's a crazy story. Because they were introduced to a lake in Canada, shallow lake. I don't know why. And essentially it was shallow, so these mysis, they don't like light. So during the day, they migrate down to the bottom of the lake. So this lake was very shallow. And so the trout in the lake could see them at the bottom of the lake and they ate them. But at night, they came up. That was what they did. At Tahoe, they migrate to the bottom of the lake where it's dark. The trout can't see them. During the night, they come up. The trout can't see them. It's dark. And that's when they eat the Daphnia and buzz miners. So that's happened in Flathead Lake. It happens in Donna Lake. I mean, dozens of lakes throughout the West. So everybody, I mean, the reason it happened is that in the shallow lake, where they could be eaten, people started catching record trout. And they prevailed upon their local fish and game departments. We want some of those shrimp, record-breaking shrimp. And so that's why we have. It didn't work anywhere but one or two shallow lakes. Question at the back there.
Right. In the example of Emerald Bay, when there was a sudden decline in the mysis concentration, was that due to particular interventions or random effects, or was it correlated to some other change in the microenvironment?
So the question was that the crash of mysis in Emerald Bay, what caused that? Why did that happen? Actually, we don't know. It was pure chance, pure serendipity that we went there in winter of 2012 to start sampling, and there were none there. That was a shock to us. We just thought they were always there. Again, I would think it was, for some reason we don't understand, some massive failure to reproduce, some whatever causes that in invertebrates, I believe happened there. And the fact that they came back indicates that it wasn't some external toxin or some Russian plot to do away with our mysis, something like that. So yeah, I wish I could answer your question more directly, but and it's interesting, but I don't know. Yes.
What's the correlation between the clarity of the lake and other health factors?
Correlation between the clarity of the lake and
Other health factors of the lake. In other words, how good is for clarity?
this is Tahoe. We don't ask that question. Clarity is good. No, actually, it's a really good question, because if you look at the amount of money that has been spent, invested in pursuit of clarity, that's a lot of roads and schools and hospitals and things. So is it just an aesthetic thing or what? Well, partly, yes. We like a blue lake. We have a multi-trillion-dollar industry. I mean, there's a lot of money that comes into Lake Tahoe because it's blue and people want it that way. But there are some health factors too. So UV radiation, which penetrates a long way down into Lake Tahoe, is a natural disinfectant. So the fact that we have, even with our reduced clarity now at 20 meters, 66 feet, 70 feet, we have a lot of natural disinfection, which means that the water that we pump out of the lake does not need to be filtered. So that's it's a cost saving for people here. Now, maybe as we start thinking about microplastics, we may want to revisit that. I don't know. We haven't analyzed that data yet. The other thing that I think is important is that UV radiation often kills the young of invasive species. So we did some experiments 12 years ago on the roof of this building, where they were collaborators from University of Miami had tanks on the roof, and they were sort of breeding native fish and warm water fish, and just exposing them to the natural radiation. The native fish high UV didn't bother them. They'd grown up here, they lived here. This is why they're here, because they can withstand it. The invasive fish, warm water fish could not take it. Maybe it's a coincidence, maybe it's not. But we didn't have very many non-native fish 30 years ago. It's a relatively recent phenomenon. And is that correlated with the decline in clarity, the decline in UV radiation? You can put in a warm water fish here and it'll survive. Whether it can reproduce is the key thing. So I would like to think that clearer water does give us an extra safety factor, a barrier against reproduction of the invasive species we have and the ones that are coming. They're going to keep coming. You.
So my understanding was that after the Lahontan trout, the native fishery was collapsed here. They introduced the salmon and the other fish that were non-native, and they threw in the mysis shrimp to feed them. And so that's why the population grew. And now that the Lahontan are being reintroduced through the Pyramid Project and what's happening at the forestry, and they've been, and I think you've been reintroducing the Daphnia population. Maybe the non-native fish have eaten mysis. There are enough of them to make it go down. They've gone up, but now with Daphnia getting a chance and the regular fish coming back, maybe there's a way to maybe that's what's happening. It's one.
Maybe. So I mean, the question was about different introductions and the like. So we're not reintroducing Daphnia.
No, I thought there was.
No, we're not. They're there. As quickly as they reproduce, the mysis are
Right, they're eating them, right.
So the lake trout were introduced, as you say, when the Lahontan cutthroat trout were pretty much fished out.
Right.
And brought them in. Which ones were left? The lake trout finished off.
Right.
But then fishermen, being what they are, they always wanted bigger and bigger fish. And so I think I don't know the exact dates, but there were many years between the introduction of the lake trout and mysis, when things were normal. So it was just the idea of wanting even bigger fish that I think created the pressure to introduce the mysis. And that didn't work.
Right.
For both kokanee, the other introduced fish, and lake trout, the state records were set prior to mysis introduction. Although Brad Allen, our boat captain, tells me that during that episode in Emerald Bay, the old state record, I think for kokanee was in 1960 something, a new state record was set in Emerald Bay. Because for a couple of years, those kokanee had been eating, whether it's Daphnia or eating the minnows that grew fatter off the Daphnia. We have photos of, but I mean, in a way, we have photos. A fisherman told us this. They're interesting stories, but they're stories. And so when I talk about the monitoring we should be doing is, we should be out, people should be out there monitoring what the fish are eating. Are the fish growing bigger? Are the algae changing? Are they, how's the system responding on a particularly dry year or wet year? Because that's the information we don't have. We have ideas. And this is our chance to do it. We may not be able to get rid of them again for another 50 years. So that's
I also want to know, when you were talking about the algae hasn't changed, but yet, I mean, all of us who lived here, 20 or more years, I mean, we have seen it more on the rocks up here than ever before. So that's confusing to me that it seems like it's definitely there when it wasn't there. But you're saying that the covered algae is the same.
Our data only goes back 25 years. Most of the development occurred prior to when the monitoring started. The mysis were introduced prior to when the monitoring started. So these changes you're talking about may well have occurred before the monitoring started. So lots of big changes, and then once we got involved 25 years ago, maybe it hasn't changed since then. I think that's a perfectly plausible explanation. You're not the only person that says that to us. Like, I grew up here, I came when I was whatever age, and it was different then. But what we're pretty sure is happening is that the areas that are affected are increasing, and that's something we can't measure now. Dr. Maloney at the back. I'm actually having a hard time hearing you.
So I remember in 2012, or I know the story about and I just find it interesting, because in 2011, it was a big winter. But it was a cold winter. And it stayed cold. Like, and you and I were like skiing up at Grouse Rock in North Canton. Memorial Day weekend, like the middle of February, big snow. So, you know, I just kind of wondered, like, temperature and runoff was just, you know, like I wondered, like, it's just kind of like a dribble, you know, it's one of the big, because I mean, basically the big lake or the lake that comes in, you know, I mean, that comes out of desolation. So that runoff is probably pretty moderate. I don't know what's been like.
So just to repeat the question, it's she's saying it was a very cold year, extreme year, 2011. Before that happened, are you saying that may have been the reason why mysis went down? Yeah, it may. I mean, something caused it. Whether it was, yeah, I don't know what, but it was clearly some factor or set of factors, but we weren't monitoring it, and that's the trouble when you're monitoring a system. Let's put this in perspective. People will ask, well, how much money do you get to monitor? It sounds like a lot of money, actually. But when you consider this is, we have 15 million visitors here, more than the 3 largest national parks combined. So there's huge pressure here. There's a huge economy. And we're talking about the sort of biological monitoring that'll be a few $100,000 a year. Oh, no, we're a $1 trillion economy, can't stand that. It's not that much that's needed when you consider the stakes. The stakes at Tahoe. You're here, you love it. Maybe you don't like all your neighbors in Airbnbs right now, but that part of the mix, and maybe we'll sort all that out, hopefully. But we have to take, it seems like there are a lot of things that we can control, but we just don't know enough. And when you don't know enough, that's when you start investing money in things that may not be the wisest use of resource. Gentlemen in the blue shirt.
Yeah, what's the name of the project for harvesting mysis? And where is it at right now?
Okay, what the project for harvesting the mysis? Okay. I certainly heard me from California Department of Fish and Wildlife. You may have heard you spoken of harvesting the mysis. Well, that was you misheard. No, there isn't. We cannot harvest mysis. We have a permit to sample mysis and count them. Are they pregnant? Blah blah blah. Do scientific measurements, but there is no permit to commercially harvest them. We have to conduct studies to see if they were harvested, if we went through at night with a net at a certain depth where the echo sounder says they are, do we inadvertently catch fish? Because if we catch fish, it's called bycatch, then that's a no-no. They're going to say too much bycatch, you can't do this. But let's say we can successfully catch them without accidentally catching fish. they may, several years from now, say, this is a safe activity, it's not harming the environment, and they will issue a permit for anybody to harvest mysis shrimp. So we're at the research stage now. I mean, there's been a lot of research done on the developing the mysis into dog treats. Different formulations, are they healthy? What's their shelf life like? Do dogs like them? We have lots of testimonials from dogs and from their owners. It's all good, but we're not harvesting them yet. But we're anticipating that may be something in the future. Does that answer your question? I didn't mean to be facetious. Shrimply blue. Oh, so that was the question? What do we do? Okay, Shrimply blue. Shrimply blue. They have a website. Hey. Maybe people would hold up their fingers to know how many words they would like in the answer. So 5 words. Yeah.
Yeah, Jeff, I came here to UC Davis somewhere around 3 years ago, and I talked to you. I didn't know you, but they referred me to you to talk to you, and I had concerns because at that time I let you know that I think it was in 2016 and 2017 at our Incline Beach, I saw acres and acres of trash floating solid, falling apart in the water, deteriorating. And you said that I wanted you to, maybe do a study on it. You said you couldn't without funding. And then it wasn't, but not too long after that, I read an article UC Davis did that they found a lot of microplastics in the sand. And until they do another study to find out where it's coming from, we're waiting. I've been waiting for that other study to find out where, because I feel like if I saw all that trash in the lake, I felt that's where it was coming from. And I pick up trash all over Tahoe, and it's coming from the land. All this trash that people leave on the land, and it blows in the lake. And will our lake be totally polluted someday if something's not done about that?
Well, that study I mentioned about at the beginning, yeah, I mean, that is trying to determine that. Like, of all the problems we have at Lake Tahoe, the little one is, and the plastics is the easiest one to solve.
Well, how is it easy?
Because it's within our power to do it. I mean, it's hard to make people pick up their trash and not use one-time plastics and things like that. But we can. We are the problem. People who use the lake, recreate on it, or on the beaches, on the trails. We can solve that. Runoff coming off the land, well, that's much harder. I mean, unlike most places where many of the plastics come in from treated wastewater, it's put back into the ocean or put in the Sacramento River or the estuary. You have no control over that happening. We don't have that at all. No wastewater goes into the lake. It's just stuff that runs off the land that people don't dispose of. So no, getting people to change old habits is really hard, but it's within our power to do it. Russ.
Tying on the flag, I got just 2 quick things. Quick. The plastics thing, the new MPDS permits with the state of California have now requested new controls for microplastics and plastics. So we've always had controls that as I run that program, and we have institutional controls, but mechanical controls. It's really difficult to control. Majority of the pollution, I believe, is actually coming from the lake itself. So activities on the lake and around the lake, and yes, there is stuff that floats through the lake. We have projects all around the lake that filter 60 micrometer and less diameter particles. And so if we're going to filter a 60 micrometer diameter, there's a darn good chance we're going to filter 5. That's the particle the state of California has required us to reduce. And over the next 10 years, we have to have full capture in order to do that. That's actually a total nightmare. And I know it sounds easy. It's a total nightmare when you're dealing with tourist populations coming here, throwing trash out and stuff flowing around. It's not easy to have that. We have Clean Tahoe program, we have League of State Lake Tahoe, that's a great program. We have the Take Care Tahoe, work with CCCs, and we send all those people out to the trash company. So there's a huge trash program in place. Where's it coming from? A lot of it could be stuff that's already there, that's kind of deteriorating, like decomposing. But just to know, like the state has actually issued that as a requirement in the next California permit, and it's a big deal, and it's a nightmare for me. Let's just say. And then Shalana, real quick, biological processes. We knew were going to be something coming up, right? It's like we got increasing lake temperatures, nutrient concentrations, upwelling. We got different types of climate or weather patterns occurring. Different types of duration, frequency, storms. I can imagine your job is kind of a nightmare trying to figure out the processes behind all that stuff. One thing I didn't hear much about was fine sediment. And fine sediment, according to like the TMDL, which is the regulating thing for the whole lake, is the particles 60 micrometer, and those particles that we're required to reduce. And so I 100% and I admire you, and I believe in everything you said. But you know, not that you're going to put me out of business with my TMDL, you know, but how does all this link together when you're dealing with a TMDL for 16 micrometer particles, where the agencies around the lake are required to reduce 72% of particulates around the lake, and then you got biological processes which are driven by nutrients, sediment, lake level, probably temperature variations, all these other things, upwelling. That could be a complicated process to like try to even model what you're dealing with when it comes to different types of algae, and then like new forms of algae. When we have the lowest record, which I showed tonight, nutrient concentrations we've measured, and all of a sudden we got blowing up new algae kind of. How do you tie this together? And is it something that we can point at? Like I agree 100%. We need to fund biological processes, which for your research. But how do you tie this together?
Okay, good questions, all of them. But where they intersect is, I think, what I alluded to before, is that development in the Tahoe Basin was coincident with the introduction of mysis and the demise of Daphnia. So the prevailing scientific lake management thought at the time was nutrients, nutrients, nutrients. That's what's causing lakes across the country, across the world to decline. And we fell into that same trap. A few years later, we found there was particles are also important, but the idea of the biology as having a control never existed. I think with what happened at Emerald Bay, the idea that maybe these organisms, some of them, the Daphnia, have the ability to remove very fine particles naturally. I mean, nobody's going to get fat eating dirt. So, but it's inadvertently, they shovel it in with the food, they excrete it as a larger particle and it sinks to the bottom. So in a way, your colleagues, all of us, I mean, I'm involved with what you guys have been doing. We've been focusing on reducing the external sources to the lake. Maybe we need to keep doing that. There's nothing wrong with that, but try to bring back that internal cleaning process. We had one example in Emerald Bay. Some people would argue, well, Emerald Bay is different to Tahoe. Maybe it is. We don't know because there wasn't enough monitoring. Now we have the chance to show whether it's right or show whether it needs improvement. So that's where it comes together. No, I would never put you out of business. I guarantee that. The last thing I would want to do, but I just think, I mean, you mentioned that the TMDL, Russ mentioned, that's a state program, it's a federal program to regulate pollutants that come into water bodies. And so Tahoe has one of these TMDLs, which says particles less than 16 microns have to be reduced. Turns out that it should have been 4 microns or 5 microns. So there's been a lot of effort and a lot of success removing particles that didn't matter. removing a 4-micron particle was exceedingly difficult, maybe not even possible. I don't know. Actually, Kenna has a question from,
Okay, from the online questions, William Bomber asks, are mice suppressed by smoke? And I would think that, I mean, just the darkness, they might get confused.
okay, good
Day or
question.
night.
So are mice suppressed by smoke? A, I don't know. But B, we did do a study many years ago when we had the fires in other fires in Yosemite. It was the Rim Fire followed by the King Fire. We were measuring zooplankton at depth. What we found was during those very smoky days back then, which are not nearly as smoky as we have now, the zooplankton didn't move up in the water. I'm not sure about mysis because they just do this whole leg thing, but the other ones didn't move up, probably because with less light, all the phytoplankton move up. So they're just following the food. Okay, we have time for one more question. Okay, that lady in the gray sweater with that hand almost touching the ceiling.
I was surprised that you didn't mention anything about the invasive species in the Tahoe Keys.
Oh,
And I was curious if you could speak to their effect on Lake Erie around what we're discussing.
okay. I heard the first part of that about invasive species and the mysis keys. You're surprised I didn't mention. Is that the thrust of the question?
Or like the effect of those invasive species on the area of the lake.
Oh, okay, sure. So, boy, if I'd have just stopped you before that question, I'd have gotten out of here without talking about the Tahoe Keys. Okay, note to self. Never take the last question. Yeah, so those of you who are not familiar with it, Tahoe Keys, among many problems it has one with invasive rooted aquatic plants, things like Eurasian water milfoil. But then, and so literally they become unnavigable. They try to control it by chopping it down, and those fragments leave the keys and grow everywhere else. They create habitat for warm water fish. So it's a whole range of invasive species problems. So there's been a project this year, a test project, a trial project within the Tahoe Keys to trial the use of herbicides. And I know nothing about the success of that. I don't think there's been any data released publicly. At least I'm not aware of any. But definitely the Tahoe Keys are a source of invasive species to the rest of the lake. But what effect that has on clarity in the rest of the lake, I don't think it's major. I mean, certainly it affects the nearshore around the rest of the lake because these plants grow in other marinas and the like, and then you start getting shading, and then you start getting these rooting non-native fish that stir up sediments. But it's for the second disc in the middle of the lake, I don't believe it's the biggest problem. Okay, so Russ Weigart wants to say goodnight to everybody.
Right, so in the report that I saw on the internet, it was talking about 16, 17 particles and how those particles are different. They've gone to the lake and they're different in the lake in the last 5 to 6 years. Can you talk to what might have happened in 16, 17, minus the meteorological effect that made those particles? And could it have been induced by like possible restoration projects or something like that?
Note to self, do not take the last two questions. So, I mean, Russ knows more about this than most people. So essentially, the key problem, one of the key drivers of clarity are very fine particles. They're there at a certain concentration in the lake, and they go up and down seasonally. And in 2017, there was that really wet year. Those of us who remember what precipitation is, huge year, one of the wettest on record. the number of particles that came into the lake, just, it was a step jump. That didn't surprise me or many other people because there was erosion of riverbeds and maybe restoration projects had been washed out. I'm not sure. So big increase in particles, and one would expect over the next 2 or 3 years that would come down. But it hasn't. It stayed at this higher level. Why? I don't know. Something we're looking at. We're starting to employ a whole new range of equipment like environmental scanning, electron microscopy, to see if the nature of these particles have changed. To see if, I mean, very fine particles, that's what we're talking about, settle out incredibly slowly. So slowly that if that's all there was involved to it, Lake Tahoe would be black because they would never settle out. They'd be stirred around forever. But they belong together, they aggregate to form bigger particles and they settle out. Something seems to be interfering with that. And that's what we're trying to find out. So before there is a third last question, I wanted to thank you all, thank Heather and Allison.